Hello, friends. This is Mechanical Vibration, free lecture 10, part 2. It is about coordinate coupling and principal coordinates. So we'll see what is coordinate coupling, what is the principal coordinate. So this thing, it is the part of 2-degree of freedom motion. So we are going to see the 2-degree of freedom motion, and it is some important terminologies. So as we see from here, this is the lace bed, which we have seen in last lecture. So we simplified schematic diagram of lace bed is like this, and the headstock part of the lace bed is considered as mass 1 and M1. The headstock part is considered M2, and the bed itself is considered as a horizontal member, what we call beam, and the short column, which supports the whole system, is considered as a column with the stiffness K1 and the K2. So, and the vibration of this mode considered as 2-degree of freedom vibration. So on that, we have x1 of t and x of t. X2 of t are the two modes of vibrations or deflection of the system from its equilibrium position. So this A and B represent the position of equilibrium. So this center line represents the position of equilibrium of the system before the excitation or before the vibration. So once it vibrates, point A goes to point A prime, point B goes to point B prime. So the distance between A to A prime taken x1 of t, and B to B prime is x2 of t. And the central point at where the center of gravity or the CG lies on represent with x of t. And this through the CG, the x of t and theta of t are the coordinates which we can use. If we are not using CG and if we are using the extreme points, then we can use x1 and x2. Or there are also another kind of representation. So this is a simplified representation to analyze the vibration. So in here, any degree of freedom system having an independent coordinates to describe the configuration. That is obviously from the definition of degree of freedom. So we have the coordinates are independent geometric quantities which measure from its equilibrium position. So this is the equilibrium position in which we are taking measurements. This A to B, the center line indicates the equilibrium position of the whole system from where we can take measurement. And each of the sets of n coordinates is called generalized coordinates. So let's consider the lace bed as shown here given in figure, and it can be replaced by the elastic beam. So we have elastic beam for portion of the lace bed, and it has short elastic column, which is represented with stiffness K and the K2. And the headstock and tailstock can be represented by two lumped masses, M1 and M2. So this is a simple representation. So this is the free body diagram of the whole system. Okay, this C1, A is a simplified schematic diagram. B is just representing or vibration model of the whole system, and then C is the free body diagram of the system. So now there are many methods to describe this motion. One is considering deflection x1 and x2 of the two ends of AB. And the second one is considering the CG as our point of analysis. So x of t and theta of t, the rotation deflection of point x, the CG point, x of t, and the rotation about the CG. That is another method of describing. The third one is deflection of x1 of t and of in A and theta of t. Or we can use x2 of t and theta of t. So a lot of methods are there. We can describe. So now, based on this, now we shall derive the equation of motion of the layers using two different sets of coordinates, either theta x coordinate or x1, x2 coordinates. So from the given alternatives, we can select one of the method and we can derive the equation of motion. So here now, we are going to select the center point. It is better to describe the equation of motion of the center point. So from this free body diagram, we can see the center moved from this point to this point. That means x of t, and it rotated about some angle theta. Okay, angle theta. So this part, the equilibrium equation of this part, x1 k1, which is equal to x1, means we have x minus L1 theta. For example, if we see from here to here, the distance from CG point here to here, which is equal to x1 of t plus L1 theta. For long, no, for short, means for small angle theta, we can directly use theta. So L1 theta is the distance from A prime to this position. And x2 is equal to x1 plus, which is x1 plus x2 is equal to x minus L2 theta. Okay, so so we have equation of motion, the general equation of motion, summation of force in the x direction, which is mx dot is equals to minus k1 x1 minus k2 x2. One thing, this thing is plus here. Why? Because this distance is equals to x1 is equals to x of t minus L1. This is correct. Okay. Here, x2 is equals to, x2 is equal to x plus. Here it is x plus this x plus L2 theta. So this one is with plus sign. So let me improve it. Here it is plus. Okay. Yeah, here it is, plus. So the summation of force in x gives us this equilibrium equation. Okay, equation A. And the second one is the moment about point O. Summation of moment about point O, or CG. That means which is equals to g theta dot, which is equal to k1 x1 L1 minus k2 x2 L2. Means the motion in, so x1 produces counterclockwise direction and x1 produces clockwise rotation. So considering that, we have this equation. So finally we can get this equation, equation B, for the moment. Okay. Now the general form of equation in matrix form will be given like this. Mass and the mass moment of inertia. This mass moment of inertia will be defined in terms of mass when we need it. So here we have x and theta coupling. Okay, So this is the stiffness matrix, K1 plus K2 minus K1 L1 minus K2 L2 minus K1 L1 minus K2 L2, K1 L1 square plus K2 L2 square. So these are the stiffness matrix, and x theta is equal to 0. So what is an elastic or static coupling? That is the point we are going to see. So if we it can be seen that each of these equilibrium contains x of t and theta of t. These are the coordinates. They become independent of each other when the coupling term x1 L1 minus x2 L2 is equal to 0. If this coupling term is given 0, that means K1 L1 minus K2 L2 are the same, then it is decoupled. Okay. The resultant motion of the laser AB is both translational and rotational when either displacement or torque is applied through the CG of the body as an initial condition. So in other words, the laser rotates in the vertical plane, and the vertical motion as well as unless K1 L1 is equal to K2 L2 means this. So this is known as elastic or static coupling. So this is the static coupling condition. What do we mean by dynamic or inertial coupling? In this case, the equation of motion using let's see the equation of motion using y of t and theta of t. What is that y of t? Look, we have here y of t from here to here. Okay, our CG is here, but in a shifted position, then some eccentric distance e from here. This is e, eccentric distance. Okay, so our reference y is taken from here, not in the exact CG position. This is the exact CG position, but the analysis is taken from some point P here. That P is away from CG by distance E, eccentricity. So during this time, we have an equation of motion like this. Okay, so after rearranging the equation of motion, finally we can get ME. This is the dynamic coupling force due to the eccentricity E. Okay, this eccentricity E resulted ME force here. So that is dynamic force. Okay, then this equation, the prime one implies the location of these things. So this is the general form of equation, and here it is represented in terms of, here it is not like this is not there. Okay, this stiffness matrix times y theta, these are the coordinates. So the equation given in the above contains y and theta, so that they are coupling equations. So they contain both static coupling and the dynamic coupling together. The static coupling is due to the presence of K1 L1 minus K2 L2 is equal to 0. Then we are uncoupling the static equation. Then we have left only the dynamic or inertial coupling. So inertial coupling means that MEY dot is the inertial coupling part. Okay. So in this case, if the laser moves up and down in the y direction, the inertial force My dot which acts through the center of gravity of the body induces motion in the theta direction by the virtue of the moment. That is Me y dot. My dot is the force, E is distance, so it is the moment. Similarly, a motion in the theta direction induces a motion of the laser in the y direction due to the force Me theta dot. So another rotational moment or torque will be produced due to the presence of m theta dot is that rotational torque, and this is the moment due to rotational moment. So let's take some particular example that illustrates this type of question, how we can use. Let's consider determine the pitch and the bounce motion of frequencies and the location of oscillations, which is the location of oscillation is known as nodes of automobile with the following data. So some data are given, mass is given, radius of gyration is given, again front axle location, distance from front axle location to center of gravity is given, rear axle location to center of gravity given, stiffness of the front is given, stiffness of the back, rear is given. So what we are expected to find the bounce and the pitching frequencies and the mode shapes, how the mode shapes characterize. So this is a representation, the bounce motion and the pitch motion about CG. The pitch is the rotation about the CG, but the bounce is the up and down vibration of the car itself. So considering this as the axis of equilibrium, so we have CG here. At the same time, the total mass of the car and the mass moment of inertia of the car is M and the G. Okay, so L1 and L2 are represented like this, and the suspension system here represent the K1 and the K2. So we can take this to this form to vibration model. So now let's develop the equation of motion. So the general equation of motion, because what we are considering here is about the center of gravity, we didn't consider the offset distance and eccentricity E. So if we directly consider the size CG, then we have this type of relation. This this part is neglected from here, 0. So this is the general form of equation, and we didn't consider any external force. So what we are considering is free vibration. If we consider some external force, we will have that part, that it is 0 here. Okay. For free vibration, we assume a harmonic solution like this. So substituting this harmonic solution into our main equation of motion, finally we get this equation. And from this equation, we directly goes to the characteristic equation or the frequency equation. Okay, so that by considering the determinant of the portion of this thing under the square bracket is equals to 0, gives us the characteristic equation. So now this is our characteristic equation from the whole system. Okay, taking this characteristic equation, we find the two frequencies, the two natural frequencies, which are omega1 square and omega2 square. So omega1 is found to be 5.8593 and omega2 is equals to 9.434. So these are the frequencies. And now substituting this frequency into the main equation means this equation. This is our equation. So substituting omega1, then we can find the first mode of vibration. Substituting omega2, we can find second mode of vibration. So, so this is our equation. So when we from this we can find two equations. Okay, so one is this, another is this. So for omega1, the amplitude ratio which is equals x over theta, gives us minus 2.6461. Just substituting omega 1 value. Omega 1 square is this value. Omega 1 square is equals to 36 point something. Omega 2 square 89 point something, like this. So substituting 34.33, finally we get minus 2.6461 is R1. Okay. Again, for omega 2, we can find R2, which is 0.3061. That is the amplitude ratio of x over theta and the second mode of vibration. So then, when we substitute those values in equation, we have this type of equation. Okay. So this implies for the first mode, we can minus 2.6461 and 1 in terms of theta 1. So that gives us this type of motion. Look, this minus 2.6461 implies from the equilibrium or from the CG position, how far it is. The node point or the point of vibration, that node point is behind of CG to 2.641. If we consider meter, it can be meter. Okay. So that would be somewhere here. So this is the node point, which is away from this 2.6461 behind. For the here actually for theta minus of 1 degree. Okay. So this is the representation. Again, in the second mode of vibration, we have 0.3061 positive, this also positive. That implies from the equilibrium position, means from CG, or from CG position is in this location. So from here, it is 0.306 meter away to the positive direction, in this direction. Okay, so the location is here, and our angle is positive also. Positive angle means, according to our representation, this is counterclock. Yeah, clockwise direction is taken as positive here. Okay, but here the movement like this, that is counterclockwise direction taken as negative in our context here. So this is the representation of the mode of pitch and the bounce. So the pitch is of the theta and the bounce is the x. Okay. The pitch and the bounce of omega 1 and omega 2 be represented like this. So the node locations can be obtained by noting that the tangent of a small angle is approximately equal to the angle itself. So this is all about the this equation. So now representing our equation, proper equation, that is one of our requirements. So x1 of t is equals to, just substituting the values of x1 and the theta relation. Okay. So we have this in terms of theta only, theta 1. Here also in terms of theta 1 only. Okay. So this is the equation of motion in the first mode and in the second mode. So from this, by superimposing the equations, this equation is this equation. That means x1 of t with x2 of t, we superimpose it. Theta 1 of t with theta 2 of t, we have to superimpose it. Then finally we can get the equation of the general equation, that the steady state equation of the system. So what will be that? x1 of t is equals to this. Okay. x2 of this. So and then substituting the equation of initial conditions, we finally find all the constants. What we have, this constant, we have this constant, again we have this constant, and this constant. All should be determined from this equilibrium, initial conditions. So applying these initial conditions, we have theta 1 equation, this theta 2 equation, phi 1, phi 2. So once we know theta 1, theta 2, then x1, x2 easily be obtained using this relation. Means x1 over theta 1 is equals to r1. So from that, we can immediately get x1. Similarly, x2 over theta 2 is equals to r2. So from this, we can find x1 and x2. So this is all about the coordinate coupling and determination of principal coordinates. So thank you very much for watching this thing. This is enough for today.